Okay, in this video, we're going to start talking about chemical bonding. We're going to talk about chemical formulas first, before we specifically talk about the two types of chemical bonding, ionic and covalent. So you should have this guided notes right here that you fill in as I go through. And the first thing, and we've talked, just did very little with bonding so far, but first thing we need to talk about is ions and what exactly are they. Well, ions are atoms that have a charge. Now, it can be positive or negative, and we know that cations are positive ions and anions are negative ions. Where does that charge come from? Well, it's going to come from a loss or gain of electrons. Now, which electrons are important? We're talking about the valence electrons, the ones in the outermost energy level. And how can you quickly determine the number of valence electrons? Is by the group number that the element's in. The group is the vertical columns, and group 1 has 1 valence electron, group 2 has 2 valence electrons. If we skipped over through the middle of the periodic table and get to group 13, which is also called group 3A, they have 3 valence electrons. Group 14 or 4A has 4 valence electrons. Group 15 or 5A have 5 valence electrons. Group 16 or 6A have 6 valence electrons. Group 7 or 7A has 7 valence electrons. Group 8 or 8A have 8 valence electrons. And these are the electrons that are important in bonding. They're the ones that atoms are going to lose or gain to try to become stable, because the reason elements try to bond to one another is because they're not stable in nature by themselves. And it all has to do with they don't have a full outer shell. So if you're going to determine the number of valence electrons that each of these elements have here, I just look at the periodic table and I go by it. Now, chlorine is in group 17 or 7A, so it's going to have 7 valence electrons. Lithium is in group 1 or 1A, that has 1. Magnesium is in group 2 or 2A, so it has 2. Nitrogen is in group 15, and it has, or 5A, it has 5 valence electrons. Hydrogen's in group 1A, so it has 1 valence electron. Carbon is in group 14, or group 4A, so it has 4. Neon is in group 18 or 8A, so it has 8. And then helium is also in group 18 or 8A, but it's the only noble gas that doesn't have 8 valence electrons. It doesn't have that many electrons. It only has 2 total. And if you notice, the first energy level can only hold 2 electrons. So helium has 2, and this first energy level is full. That's why, the noble gases are stable by themselves. They don't want to react with other elements because they're stable. All the other elements want to react because they're not stable in nature by themselves. So we rarely find elements by themselves in nature. They're usually bonded with another element in a compound, and that's because of stability. Now, the Lewis dot structures are just diagrams that show valence electrons, and I show that with dots around it. So if I want to draw that for lithium, I would put the symbol, and And then I want to put dots around there to show the valence electron. It only has one, so I would draw it like that. Magnesium, it's in group 2A, it has 2 valence electrons. I would want to draw it with 2 valence electrons like that. And there's a specific way you're supposed to go counterclockwise, but we're only doing this to show valence electrons. We're not going to be that specific about it. Okay, boron is in group 13 or 3A, so it has 3 valence electrons. So I could show those as like that. Silicon is in group 4A, so it has 4 valence electrons. So I would show it like that. Nitrogen is in group 15 or 5A. And then I would start back over, putting one right there. And then sulfur's in group 6A, or 16, 6A. It has 6 valence electrons. And fluorine is in group 17 or 7A, so it has 7 valence electrons. And then last, neon. It's in group 18 or 8A, so it has 8 valence electrons. I'll show 2 of them on this side. And that just shows you there's nowhere else to put any dots around there. It's full, and so when we use these little dot structures to show how elements gain or lose electrons to fill their outer energy levels. And this neon doesn't have any places left for electrons to go. So the octet rule says that atoms want to be stable. And which group of elements is the most stable? Well, it's the ones that have a full outer energy level, which is the noble gases. They have 8 valence electrons. They don't need any more. What's the octet rule say? You need 8 electrons in the outer shell to be full. Atoms seek to achieve the electron configurations of noble gases. All elements want to be like the noble gases. And how can atoms achieve an octet? Well, there's a few different ways. They can lose electrons. For example, metals tend to have just a few electrons at our energy level. It makes more sense for those to lose those electrons and then to gain a bunch of them. It takes less energy to lose one so that your next energy level is full than to gain 7 to have 8. So and nonmetals have 5 or more electrons in their outer energy level. It makes more sense for them to gain 1, 2, or 3 electrons to become stable. So they can either do it by losing, gaining, or one other way would be to share electrons. Okay, next for this part right here, before we start filling that in, one thing I want you to do is go in, and this was something that I didn't catch. Just mark that out right there. We're going to fill that in with this right here. First, a chemical formula is a symbolic way to represent compounds. We use symbols as a shorthand way of doing that instead of writing it out all the time. You know, we've come up with a system of doing this. Now the symbols have letters in them, which chemical symbols do for elements, shorthand way of writing those. These chemical formulas are show two or more elements combined. And the chemical symbol represents the elements that are in a compound. And each new capital letter represents a new element. Now, subscripts, those are small numbers on the lower right of the chemical symbol. If you notice, if we look at an example like CO2, these subscripts are written as, to tell the number of atoms. In this case, carbon would have doesn't have a subscript, so no subscript means there's only one atom of the compound. It means there's only one carbon. It's just understood. We don't have to write the one. And then there would be two oxygens, and that compound is carbon dioxide. Now, if I'm going too fast, you might stop the video to fill these in before we move on. Now, for the parenthesis part of the chemical formula, when present, subscript on the outside multiplies by all the subscripts on the inside to determine the number of atoms. So, for example, if we have something like, you'll see chemical formulas like this sometimes. And what that means is, in this case, we would have one calcium, and then the 2 on that multiplies by everything on the inside. So on the inside you have one oxygen, you have one hydrogen. Well, that would be 1 times 2, you'd have 2 oxygens, and 2 times 1, you'd have 2 hydrogens. is a reason why we write it in this form right here that we'll talk about later on. Alright, so let's look at this example. What elements are present in the compound? We have H2SO4, and the actual name of that compound is sulfuric acid. Well, we have hydrogen. S stands for sulfur. O stands for oxygen. How many atoms of each element are present in the compound? Well, the subscripts go there. I got a 2 hydrogen, so I would have 2 hydrogens. Sulfur, there's not a number there, so it's understood as to be 1. You have 1 sulfur. And then that 4, you have 4 oxygen atoms. And what's the ratio of elements in the compound? Well, the ratio would just be the same thing. You have 2 hydrogens for every 1 sulfur for every 4 oxygens. Now there's a difference when we write as a subscript. For example, if we have O2, that's a subscript saying we have 2 oxygen atoms. In this case, it would be 2 oxygens bonded together, 2 atoms bonded together. As an ion, we write them differently. We write as a superscript, meaning an oxygen forms a 2 minus ion. We'll talk more about those later. That doesn't mean 2 atoms of oxygen. That means that oxygen needs 2 electrons to be stable. It's going to get, whenever it gets 2 electrons, usually from a metal, it has 2 more electrons than it normally has, than it has protons. So it forms a -2 charge, or we call it a 2 negative charge. So that 2 minus tells you the charge of oxygen when it gains 2 electrons. It's different than a subscript. People get those confused, so you have to be very careful. Okay, our next example, we have MgOH2. This is magnesium hydroxide. This is whenever magnesium, oxygen, and hydrogen form a bond. What elements are present? Magnesium, oxygen, hydrogen. How many atoms of each element present in the compound? Well, there's 1 magnesium, because there's not 1 there, so it's understood. But you have 1 magnesium. Oxygen, you got 1 on the inside of parentheses, times 2, gives you 2 oxygens. And then hydrogen, there's 1 on the inside, you multiply by 2, and they give you 2 hydrogens. And then the ratio is this, we'd write it like this: 1 magnesium for every 2 oxygens for every 2 hydrogens. Now we get to this last page. It's kind of a review before Thanksgiving. We went over ionic and covalent compounds just a little. Ionic means when electrons are transferred. There's a transfer of electrons between elements to form ionic bonds between a metal and a non-metal. Covalence when electrons are shared. Remember, it's the valence electrons that are going to be shared or transferred. And it's between 2 or more non-metals. So if we can look at a compound, its formula, and we can tell if it's ionic or covalent. There's a way of doing this based on electronegativity. That was something we talked about in the last unit. ability of an atom to attract electrons, and nonmetals are a lot more electronegative than metals. Small metals lose electrons and nonmetals gain them. And you can calculate the values and subtract them for a metal and nonmetal, and if it's a certain value, it'll tell you that's covalent or it's ionic. And we'll look at that when we talk about polar covalent bonds a little bit later on. It might be after Christmas. But right now, we're going to just use if it's a metal and a nonmetal. If the metals are to the left side of the stereostep line, nonmetals are to the right side of the stereostep line. That's to determine, what we're dealing with. So if we look at this first example, you have sodium, and you always look at the first element, and it's a metal. Chlorine's a nonmetal. If the first element is a metal, then it's an ionic compound. If the first element, like in number 2, is a nonmetal, like in this case, CO, it's got carbon and oxygen, carbon is a nonmetal, it's going to be covalent. The second element's always going to be a nonmetal. Next we look at H2O. If we look at H, and go, well, that's on the left side of the periodic table, but it's our one exception. Hydrogen is a nonmetal. We place it in first group for certain reasons, but it is a nonmetal. So H2O, water, is a covalent compound. Number 4 is the strontium fluoride. Strontium is in group 2A. It's in metal, so this would be ionic. Next compound, LiOH. Well, the first one is a metal, lithium. The next 2 are nonmetals. So this would be ionic. Number 6, N3BR5. N is nitrogen. It is a nonmetal. So on the right side of the stereostep line, this would be covalent. Number 7, first element, silicon, is a nonmetal. It's on the right side of the stereostep line. So this will be a covalent compound. Number 8, first element is aluminum. It is a metal. It's on the left side of the stereostep line, so this would be an ionic compound. Remember, the second, third elements are always going to be nonmetals. So we always look at the first element. If it's metal, it's ionic. Non-metal, it's covalent. We look at number 9, pH3. If you look at P, it's phosphorus. It's to the right of the stereostep line. It's a nonmetal, so this will make this a covalent compound. Then number 10, we have this first element is zinc. It's to the left of the stereostep line. It's a metal, so this would be ionic.